Okay, hello, I'm Michał, and not surprisingly, I'm from Wrocław, as Agnieszka mentioned. So today, I will try to tell you some of our recent results regarding this telegraphic multifractional Brownian motion, which the name is complicated, but I will try to present it as easily as possible. So this is joint work with Agnieszka Balcerek here, with Professor Krzysztof Brudnecki from Wrocław, with Professor Aleksiej Czeczkin from Wrocław and from Potsdam, and Simon Tapa from Dresden currently, and Ralf Metzger from Potsdam. Okay, so first maybe few words about the motivation. So the motivation comes from the so-called anomalous diffusion processes. And this is a term mostly used in physics. And in the scope of this talk, the anomalous diffusion process means that a stochastic process that has nonlinear behavior of the second mode. So as you can see, nonlinear is specifically power law behavior. And so the sum of the nomenclature, if the power, so if the exponent a is greater than 1, we call it superdiffusion, because we understand as this process is, let's say, or moves faster than classical diffusion. And when a is smaller than 1, of course positive, then it's called subdiffusion as it is, let's say, slower than classical diffusion. So if a is 1, we call it normal diffusion, and one of the most well-known examples is, of course, Brownian motion, where this proportionality is, let's say, exact. And why do we need this anomalous diffusion processes or models? It is because they are widely observed in different applications. So the closest to me are, let's say, the biological applications when we measure some movement particles within a cell. So it can be proteins, it can be, let's say, something connected with DNA, so telomeres.
Telomeres are responsible for aging, right?
Of course, yes. So you would like to know, for example, when they move fast or when they move slow, or whether it's connected with, say, aging, right? Or if we can control it. But of course, we can go, instead of considering nanoscale, we can go, let's say, higher, so consider some maybe transport through porous media, so some levels of some liquid, or even higher, so animal movements. So birds fly all the time, so when they, for example, travel during the winter, their movement can be also described by some type of anomalous diffusion process. And maybe one last, let's say, example, some intangibles, so like finance, or modeling stock prices, for example, or cryptocurrencies, let's say prices. Okay, right. Okay, so as I said, biological experiments are closest to me. I have the most experience with them. And this is a frame, on your left. You see a frame from a movie that was recorded. So the whiter spots correspond to labeled particles within a single cell. Labeling is done by attaching basically some fluorescent thing to this particle, protein, for example. And then using some software, we can try to track it. Of course, this is much more complicated than these two sentences. But the methodology is quite developed, and currently, for example, some machine learning methods are used to do that. So in the end, we have many frames, so we can try to track a single particle through many frames, and after that, we have some data, and mathematicians come and try to say that, okay, this particle moves like that and that. Which is quite interesting topic, because practitioners, let's say biologists, doctors, can, let's say, infer some information from the type of movement. So, but if it's moving faster, then it's better, for example, to apply some medicine in the cell. Okay, so this is already pre-processed data, and AB plots A, B, and C are some different let's say experiments or different types of particles, and you can see they behave in a very different way, even in the same cell. So, for example, like let's focus maybe on this B, this let's say red blob, basically corresponds to a particle that stays in the same place. But of course, there are, let's say, some particles that tend to move quite far. And yeah, so we would like to have some methodology to distinguish. And the bottom right plot, the plot D, is a plot of this mean square displacement. So the second moment with respect to lag time of time. And as you can see, this is in log-log scale, so straight lines correspond to power law. So as you can see, this, let's say, more or less straight lines also have different slopes. So there are, let's say, straight lines that behave almost like this dashed line, which corresponds to normal diffusion. But there are also, let's say, lines that are almost horizontal. So basically, they correspond to cases where the particle isn't moving. So again, quite various types or many types of behavior. So maybe let's go to mathematics. So one of the, let's say, most popular models that describe anomalous diffusion is the so-called fractional Brownian motion. So this is an extension of this Brownian motion of Wiener process, where we use some additional parameter h, which is called Hurst's parameter, Hurst's exponent, or self-similarity parameter. And well, the model is this can be described as this, let's say, moving average representation. There are, of course, many different types of representations, but here's one of them. This model, let's say, comes back to Kolmogorov and then Mandelbrot and von Ness, quite famous names. So, let's say, following this observation from the previous slide that we have different types of behavior, even in a single cell, even in a single experiment, we thought that having a single H to describe all of the trajectories is too restrictive. And like in this paper from last year with Agnieszka and others, we considered using random H. We considered, so basically we put some a priori distribution H. We considered different distributions from discrete distributions like 2-point distribution to continuous distributions. We calculated some stuff like I don't know, PDF of this process, mean square displacement, and so on and so forth. But we didn't stop there. And the next part of the story is the so-called telegraphic multifractional Brownian motion. So maybe let's focus first on this multifractional Brownian, because on previous slide it was fractional. So what changed? So by saying this is multifractional Brownian motion, I mean that now the previously constant h now is a function, deterministic function. For the process to have, let's say, nice mathematical properties, we would like for this h to be a Hölder continuous function, exponent, and for even better mathematical properties, we now use this harmonizable representation of the process. Okay, and then under these assumptions, under this representation, like in the, let's say, early 2000s, Ayash, Cohen, and others proved that this process has the following auto-covariance function, of course, if the normalization constant is proper. Then we have the following auto-covariance function, and if H is constant, then it coincides with the previous fractional Brownian motion. Great. And H now, let's say, controls the local behavior. Previously, it controlled, let's say, global behavior. H is constant, it's global. Now, H controls this, let's say, this, for example, self-similarity, but locally. So what we did, we considered, so it was a natural, let's say, way of progress. So instead of considering constant H, or sorry, functional H, we considered H as a stochastic process. Of course, again, for nice mathematical properties, the process it's good for the process to be continuous, for example. So again, the only change is that H is a stationary again for nice mathematical properties. H is a stochastic process. What else? Here is a general definition of the so-called multifractional Brownian motion with random first exponent, even first name. But because, again, we work a lot with some practitioners, like biologists, an idea was to consider some, let's say, maybe simpler cases. For example, simpler cases meaning not a general H, but some specific H. And the easiest way to create a process that has not that many states is to consider a telegraph process. So Markov process that has two states, and the states change with exponential distribution. So we stay in one state with some exponential time with rate lambda 1, 2. Then we go to lambda to 1, and we stay, then we go to H2, and we stay in H2 with exponential distribution with rate lambda to 1. But this process is not continuous, yeah, to states, it only jumps. So we considered a so-called smooth telegraph process. And this is, the so-called smooth telegraph process is given by this stochastic differential equation, in which we have some additional parameter delta. And this delta controls the speed of going to another level. I will show you a plot of some trajectories in a second. So, for example, one of the results that we found is that we were able to find, for example, stationary distribution of this smooth telegraph process, and it's actually beta distribution. Of course, rescaled to interval H1 and H2, but still it's beta distributed. And the exponents or the parameters of this are given, are known. So, okay, so finally I can show you some trajectories, and of course, beta distribution has basically two main behaviors. It can be either unimodal or bimodal, let's say, for sake of simplicity. So, so PDF of some beta distribution is either in the top right-hand set or bottom right-hand set. So unimodal or bimodal. And the corresponding this smooth telegraph process look like this. So we basically go to a level with some speed. Let's consider this yellow line. We go to a level with some speed, and then after some, after some exponential time, we start going to next level with the same speed, and so on and so forth. So we switch back and forth between these levels. So in bimodal, we tend to, let's say, stay close to the limiting levels a lot more. But on the other hand, in bimodal case, in unimodal case, the blue one, well, we switch our, let's say, levels that fast that we basically don't reach our limits. So that's completely different behavior, which we found quite interesting. So the corresponding trajectories of this TEMBM, so the graphic multifractional Brownian motion, are, let's say, two top trajectories on the right-hand side of the plot. So the blue line, like for the people that don't have that much experience, let's say, even for me as well, it's actually hard to say if anything changes within the trajectory. Even that, we know that this underlying age changes. It's much easier, for example, to spot the changes on this yellow trajectory when we first start by having this quite smooth trajectory with low, let's say, local variance, which corresponds to, let's say, this high level. But then we have this not smooth part of the trajectory with high local variance, which corresponds to this small local age. And the trajectories below correspond to classical fractional Brownian motion with h being the low limit, so 0.1. This is the middle, so 0.45, I believe. And the bottom trajectory corresponds to the top limit, so 0.8. So as you can see, the trajectories, specifically this yellow trajectory, inherits some of the parts of this, let's say, subdiffusion, so fractional Brownian motion with low h, and some of the parts of this superdiffusion, so FBM with high h. That's okay. So that's all nice. Model is just a model. But then the question came up: how to distinguish this model? So how to identify this model in the data? How to distinguish whether we have constant age, whether we have random variable age, or whether we have stochastic process age within the same, let's say, scope of fractional or multifractional Brownian motion. And we came up with let's say, algorithm or methodology that by using our knowledge that this age process corresponds to this local self-similarity or local smoothness, we can estimate this age by considering only a part of our, let's say, observed trajectory. So we call this a window of fixed length W. And from this window, we estimate, let's say, first age. So the age in first time point, let's say. And we do for the whole trajectory. And we do that for each trajectory that we observe. So in the end, we have, for each trajectory, we have this, let's say, trajectory of estimators. And we have many trajectories. So what we came up with okay, maybe I will tell you in a second. Not yet. Surprise for the last. Okay, so does this methodology work? Well, I think it works. So here you can see that we compared the three things. So we fixed some time here. Yeah, we fixed some time. And we got a histogram of this estimated age in this fixed. Then, so this is the blue bars. Then we plotted this orange line, which was the beta density, so the stationary density of the model. And on top of that, this green bars correspond to the ground truth. So the true age which we simulated with. So I guess the three cases coincide quite nicely. So we, in neither case, we make big errors. So in this bimodal case, it's a little worse, let's say, because we do some errors, let's say, near the limits, but we think it's, let's say, good enough. Because, of course, the estimators always can be improved, for example. And, okay, so this is, say, visual proof that this methodology works. But what about differentiation between the models? So what we did, so by having this many trajectories of these estimators, we just tried to, let's say, calculate the covariance between, let's say, the first point and so autocovariance of age, estimators of age. So covariance between age in T1 and age in T1 plus some lag, based on these many trajectories that we observed. And actually, this methodology resulted in a surprisingly good, let's say, plot. It's a surprisingly good way to differentiate these three cases. Because maybe let's focus here first on the green line, which corresponds to this fractional Brownian motion when h is constant. So it makes sense that that our estimators should estimate constant most of the time, or like near this constant most of the time, and the errors of this estimator should not be much correlated, so that the covariance should decay to zero quite quickly. This vertical line corresponds to the window length. So after lag is bigger than the window length, we have two disjoint. So we have covariance of estimators based on two disjoint samples. Okay. Then maybe go to this top line, purple line. So this is this fractional Brownian motion with random exponents. So random as in random variable. And actually, after this, let's say, window size, it stabilizes at a fixed level. And it did this, let's say, stabilization behavior did not depend on the type of distribution of age. So whether we have this 2-point distribution or beta distribution or whatever we came up with, we had this stabilization, not necessarily, of course, on the same level, but we have this stabilization. And now we come to this telegraphic multifractional Brownian motion. And we see that the autocovariance of these estimators actually decays exponentially. Okay. So on the level of model, it works. That's great. Oh, sorry, not yet. But what's on the level of data? Because I said that I needed to have some applications. So we considered 4 different data sets from various, let's say, applications. So for example, the first one, so the blue line, that tends to be around 0, corresponds to some temperature data. So temperature data, not the temperature that we observe, but the deviations from the, let's say, long time mean. So having each month, having temperature, let's say today, we subtract the mean temperature of 14th of September. This is the observation of multiple years, the previous multiple years. And of course, in order to have, let's say, many trajectories so that we could calculate this autocovariance function, we have to split the data in single years, I believe. So what let's say this plot suggests that this data follows fractional Brownian motion. And actually, there are some papers that claim the same. So That's good information. What else? Let's consider data set 2 and 3. So these two guys. And these two are the, let's say, experiments from biology, so single particle movements. And again, this autocovariance function seems to stabilize at some level. But it's the same level, it's coincidence, these are two different experiments. But again, it suggests that we have this fractional Brownian motion, but with random exponent. And the fourth data set, this one, is again, yet again, different type of data. It's electricity prices. 15 minutes. So the electricity prices recorded every 15 minutes, let's say for 1 year. And each trajectory here was 1 week. So the electricity prices were from last year, from January. And it seems to be working. So yeah, so I think that's quite, well, good methodology. Of course, so far we only checked how this methodology works within the scope of this model, so telegraphic multifractional Brownian motion. But of course, we plan to extend our research further. Okay, so that's all. So thank you very much.